Hi students, I hope you're all doing well. So welcome to this lecture on region-based segmentation. So when you started this module on segmentation, I told that segmentation can be done using two properties. One is based on discontinuity property and one more is based on similarity property. So previously when we saw how we can use discontinuity to perform segmentation, right? So what did we do? We found that whenever the boundaries between the regions are based on discontinuities in intensity level, we can determine the segments or objects. So we went for point, line, and edge-based segmentation, right? Okay. Also, previously in few of the previous classes, HOD ma'am has explained how we can perform segmentation using threshold based on the distribution of some pixel properties. So it could be based on some threshold based on intensity value or color values and so on. So we should define some property based on which we can perform segmentation. So broadly, we can say that segmentation can be performed using either discontinuity-based segmentation or similarity-based segmentation. So when we perform region-based segmentation, we are actually using the second property, that is based on similarity, right? So let us see now in this lecture how we can go for region-based segmentation and which are the few algorithms or methods which you're going to study. So let's proceed. So under region-based segmentation, you're going to study two techniques. The first one is called as region growing and the second one is region splitting and merging. So both of these are based on region-based segmentation. Okay. So as the name suggests, region growing. Region growing. So what you can think of, so when you plant a seed, so it grows. When you plant a seed, it grows and then it becomes a plant. Okay, it becomes a single plant. So same way here region growing is a procedure which groups the pixels or subregions into larger regions based on some predefined criteria for growth. For example, let us speak in very simple points. So suppose I have a pixel. Okay, I started with a pixel. Okay, this pixel will be called as the seed point or the seed pixel. Okay, so from this seed point, what I do is I'll check the neighboring pixel. If I feel that the neighboring pixel is in some way or based on some criteria, it is same as that of the seed pixel. Okay, so suppose I have a pixel. Okay, I check the neighbor. Okay, the neighbor pixel, if it has got some it satisfies some criteria, or if it is some way similar to the previous pixel or the seed pixel, I will club this to as one region. Okay, next I go to one more. I see the next pixel. I see the next pixel in the neighborhood. So already you have studied about connectivity, right? Okay, so let me check everything in the 8 connectivity region. Okay, so if I feel that there are some pixels which are identical or similar to some based on some predefined criteria to the previous pixel, then I can say that it belongs to the same region. This is how I grow the region. Okay, so as the name suggests, region growing is a procedure which helps to group the pixels or subregions into larger regions. So I keep on growing. You are similar to me. Okay, you come to me. You join me, or like that. Okay. So here, basically, as I told you, we start with set of what is known as seed points, and from there, we check the neighbor pixel, and based on some property, we will we'll club them to one sub-region or we grow to a larger region. Now, selecting one or more starting points can be, it depends on the nature of the problem as to what kind of segment I am trying to, club together like that. So usually, a priori information may be available. If at all the a priori information is not available, then the procedure is to compute at every pixel the same set of properties. So ultimately, we're going to use it to assign pixels to regions during the growing process. So I think by now you understood that here region growing is based on similarity, not on dissimilarity. That's why I said region based segmentation is based on similarity measure or similarity property. Now there is a reason or there is a means of selecting this similarity criteria. So this similarity criteria based on which I group certain pixels. Okay, so I use some criteria, similarity criteria. So if these pixels are similar, I group them to one region like that. Okay, it does not only depend on the problem under consideration, but also on the image data available. For example, if the problem under study is you are trying to analyze some satellite image land use data. Okay, depending on some type of color, you can see that sometimes pseudo color is used some way. Okay, so the problem would become significantly difficult to solve without some information available in the color images. Okay, so we need to sometimes have some prior information about the image data. So, for such cases, especially when you're going for some satellite images and all, classifying into some group or similarity based criterion is not always possible unless you have some data available related to the similarity or clubbing. So that is one thing. So sometimes when the images are monochrome, so then how we can do the region analysis? Then we use something what is known as descriptors. Okay, so descriptors which we'll be studying in more detail in the next lecture. Okay, but descriptors itself by itself sometimes it may not result into the kind of connectivity we require. Okay, so sometimes that may not be cannot happen. Okay, so descriptors which we'll study sooner. So we can use descriptors also for region growing, but that is not always the best solution. So there is one of the major problem is defining the similarity criteria. Okay, and it only not only depends on the problem under consideration, it also depends on the image data available or the prior information available. One more problem when it comes to region growing is the stopping rule. Okay, I keep on growing. When to stop? Okay, so I should have something known as a stopping criteria. Okay, so basically this is usually defined when no more pixels satisfy the current criteria for inclusion in that region. So usually the kind of what to say descriptions or the kind of criteria we use will be usually what intensity value. Okay, if this is close by, if the intensity value is close by, let me group it into one region. Or texture or color, whether the color variation is to some extent close by. So all these things are taken into consideration, and if it is not matching that, then we will stop the grouping. Correct. So sometimes additional criteria can be used, to enhance or sophisticate the, to make the region growing much more efficient and to club properly. Okay, all the pixels which belong to one particular segment. Okay. So that is about some of the things which we need to understand when it comes to region-based segmentation based on region growing. So how to define the algorithm for region growing? So what we have discussed till now, the same thing which you are going to put in some points. Okay, so let the f of x comma y denote the input image. Okay, and let that point let us define an array which is known as a seed array. Let s of x comma y denote a seed array. Okay, let the seed array contain only containing ones. Okay, at the locations of seed points and zeros elsewhere. As I told you, there may not be one seed point. The number of seed points depend on how many objects you want to segment, or how many segments you want to have. So in one image itself, I can have many starting seed points. Okay, from there I keep growing and forming the segments or forming some similar regions. Okay. So let me denote s of x comma y as that seed array consisting of which is ones, and at the location where the seed points are there and zero otherwise. Okay, and I told you in the first class what is known as predicate. Okay, so let q denote a predicate to be applied at each location x comma y. Okay, so arrays are assumed to be of same size. Also basic region growing algorithm where we are going to use 8 connectivity, it is stated as follows. Okay, so the first step, so connect all the, or find all the connected components in x of xy. Okay, all the connected components. You know what is meant by connecting. Okay. So and erode each connected component to one pixel. So label all such pixels as 1 and label all other pixels as 0. Okay, so that's what based on some criteria, I'll find all the connected components in S of xy and erode each connected component to one pixel. Then I form an image by name FQ such that At a pair of coordinates x comma y, let fq of x comma y is equal to 1 if the input image satisfies the given predicate at those coordinates. Otherwise, that fq of x comma y make it 0. Okay. So what did we do? I'm going to check each pixel one by one at the location of the location. What is that location? X comma y for all x comma y. If it satisfies the given predicate, that value I'm going to make it 1, else I'm going to make it 0. Now, the new image, let it be G, be the image formed by appending to each seed point. So, if I have 5 seed points, I keep on growing that 5 points and make it 5 regions, right? So, I'm going to append to each seed point in S all the one valued points in that 8 connected region to that seed point. Okay. Then I'm going to label this as point 1, point 2, point 3, point 4, point 5. Or I can say this is starting, see each region I'm going to label it as 1, 2, 3, 4. So suppose I started from 4 seed points, 4 like that. Okay, so label each connected component in with the different region label. For example, 1, 2, 3 like that. Okay, so this is a segment image that is obtained by region growing. So what you're studying now is a very simple algorithm. That's enough for now. Okay, so we are labeled them and we keep growing them. Okay. So let us see with an example how we can use region-based segmentation. So how we can go with the algorithm we just studied. So here is an example of a X-ray image. Actually, what you can see, that first image is of, you can see some crack, right? Yes. So this is the image of a weld. Okay. So if you have a welded or, some welded region, there in that welded region, there is a crack. So this X-ray image shows the welded crack and porosite region. So we are trying to use here, a region growing technique to find or segment the defective weld regions. Okay. So first what we have to do is we need to determine the seed point. Okay. So seed point is from where we start or where we start labeling or we assign different seed points, right? Okay. What here we can come from a prior information is that the cracks and porosities, if it is present, it will attenuate the X-ray signal. Okay, so that is what we did. So we can observe that it has attenuated the cracks have attenuated the porocytes, they have attenuated the X-ray region. Okay. So what you can see here, the figure B is actually the histogram. That's the histogram of the original image or the X-ray image. So why we usually use histogram is that we can see where, we can apply some thresholding or some sort of such, method to perform segmentation. Okay. So we just found the histogram. Okay, then what we are doing in this example is we apply threshold, okay, to extract the seed points from the original image. So here what we are trying to do is, okay, so here in the figure B is the histogram and what you see here is actually the seed image. Okay, so what you can see here is the initial seed image by applying the thresholding. So what is thresholding? So what is the percentage we have used for thresholding? So since it was initially a grayscale image, so grayscale image means it's if it's an 8-bit, so it is 0 to 255. So let me use a high percentile of the thresholding. So 99.9 percentage of the maximum. So 255 is 99.9 percentage is 254. So whatever is above 254, make it white. Below that, make it black. So based on that, we have found this image C. Okay, so you can find that there are some points here. Okay, so this is called as the initial seed image. Okay, so then the image B is actually, I don't know if you can see in the textbook, there I can see some small dots. This is actually the result of morphological encode eroding. Okay, so then we have to define a predicate operation, right? So what you see here is the predicate operation. So what we are interested is in appending to each of the seed points. So we have found the seed points. Okay, we have found some 3 to 4 seed points. So we are interested in appending to each of the seed point all the pixels that are 8 connected to that seed and are similar to it. So we are going for 8 connectivity and all the pixels which are similar to it. So they are grouped as one region. Okay, so what is the predicate we are trying to do is Q is equal to true if the absolute difference of the intensities between the seed and the pixel of point of consideration at x comma y is less than or equal to t. So where t is some positive threshold, it is false otherwise. So we're going to see, okay, some threshold point, threshold t we are going to take. What is that threshold? We will see sooner in this example. So let me take the t value. So if the difference between the intensity of the pixels of the seed and the point of our interest, which we are checking, if the difference is less than threshold, then we call the predicate to be true, or here we consider it to be part of the region, else we consider it as false. So after doing that, what we find here in figure E is the absolute value of the difference between figure A and C. So what you see here is actually the absolute value, okay, absolute value of the difference between the figure A and C. Okay, so that is figure E. And figure C, D, E, F is actually the histogram, correct? So what you can see is the histogram of this figure E. Okay, so then what do we do? Okay, so F is the histogram, A, B, C, D, E, F. F is done. Okay. Then what we do is we will use a sort of thresholding to use in the predicate. So why we apply predicate is to establish similarity, right? So we have started from the seed and we need to grow from the seed value. Okay. So if at all the difference is less than threshold, we merge it to that. We combine the labeling or we merge it to the same region. Else we don't consider it to be a part of the region. Correct? As simple as that. Okay. So here what we have done in the figure DFG. Okay. So figure G is that we have applied a dual threshold. So here dual thresholding is we have applied the T1 threshold to be 68 in this example and T2 to be 126. So we say that if it is about, I have already explained if in one of the classes how to go for dual thresholding. So with the same concept here, dual thresholding is used with T168 and T2 126, and we find that we are not able to actually get any much information from applying dual thresholding. So let us go for single thresholding. Okay. So here in the next case, we are going to apply only single thresholding, where smallest of the dual thresholding is used, and we have got this result. And then the figure I is by from how we go for region growing. Okay, so here we have combined the concept of thresholding and also we have applied region growing. Okay, so we have found the seed points, we have grown the seed points using the predicate, and to make the segmentation using region growing even more fruitful, we'll also apply thresholding. So by applying a single thresholding, we found that, and by using that particular predicate for seed growing, we found the final one to be the place where only the cracks can be visible. I hope you understood the simple point. So what we did is we first took the image. We are using the histogram to determine at some threshold values. Okay, it could be T1, T2, or a single T1, T1, T, etc. And then what we have done is we have found the predicate. So the predicate, if it is true, group it into, or make it a part of the initial seed from where we have started, else discarded. And then we have used instead of, we checked with dual threshold, which didn't work out, and just with single threshold it worked out. And this is how we can use thresholding along with region growing to determine cracks in the X-ray image of a welded crack, of a welded image of a welded object. Okay, so this is one example. So with this, we will wind up the discussion on region growing. So next, the discussion is going to be on region splitting and merging. So in region growing, what did we do? We started with the seed point. So if the neighboring connected pixel, if it is connected in some sense, or if it is having some intensity value similar, or based on some predicate, if they have some similarity with the previous pixel, then we will combine it to that region, as we do not combine. And then we should have some stopping rule, wherein if the criterion is not satisfied, you stop the growing procedure. Okay, so this is what we have studied in a very simple way. There are much problems that could be encountered, so we're not going to advanced level of thinking how region growing can be applied. So with this we end region growing. So let us get to the concept of region splitting and merging. So now let us try to understand what is meant by region splitting and merging. Okay, so previously you studied about region growing, right? So now it is quite the complementary of that, wherein we go for region splitting, and then after some condition we will go for merging. Okay. So when we do this splitting, okay, so we split into small, disjoint regions, okay, and each of this region we try to see through that almost they have some similarity, because here when we go for region-based segmentation, we are very much particular about the predicate which we are using or some sort of predefined criteria. So basically, to summarize, region splitting means subdividing an image initially into some set of disjoint or arbitrary regions, and then when we come to merging, we merge it to satisfy the conditions of segmentation. So basically, we merge or split the regions to into some disjoint regions, and finally we should get some meaningful segments. So that is what is the idea behind region splitting and merging. Now, how do we go about doing this? I think by now you might have got the idea. Okay, so rather than going for region growing, so we're going for region splitting. So in region growing, what did we do? We started from one point, and nearby, if it is having some common, we will identify some seed points, right? So some seed pixel, and then we start growing based on some predicate condition or some predefined condition. So we start from small and grow till the entire image. Here it's the opposite. That is, we start from the entire image and keep on splitting keep on splitting the image into small regions, and then maybe two or three. Suppose I have divided one whole image into 10 regions. Maybe two, three regions. I may club to form one region. Another four, five regions to one more region. Basically, as one segment. Okay. So this is what I'm trying to tell. So let R represent the entire image, and we will select some predicate. Okay, so based on which we will go for splitting or we'll go for merging. Okay, so it can have its own predicate. So first what we'll do is we'll segment or subdivide successively into smaller quadrants. Okay, so quadrants we mean that it's a section of 4. Okay, so what you can see here is an image of the same. Okay, so we took an image. Okay, so we divided into first initially 4 regions. Okay, you can see that there are 4 regions. R1, R2, R3, R4. Again, maybe R4 can be subdivided again into 4 more regions, that is R41, R42, R43, R44. So depending on the type of data we are trying to analyze. Okay. So same way, this is how we are going to represent a partitioned image. So this could be one segment, this could be one segment, this could be one segment, this one, this one, this one, this one. And maybe sometimes what will happen is R2 and R41, for example, may belong to one segment. So after splitting, I may go for merging of, say, for example, R2 and R41 can be combined to form one region maybe. Then R43, R44 and R3 may be, merged to form one more region. So this is what we show is splitting. So then if you ask me what is merging, then maybe, based on some criteria, I may have to again merge them. Okay, so merge which regions so that they form some meaningful segments. Okay. So this is how we represent a partitioned image. The same way you can represent it using what is known as a quad tree. Okay, so R, the entire image R, we can divide it into, what did we do? R1, R2, R3, R4, and R4 maybe I have divided. So this is how we can represent using a quad tree for region splitting. Okay, so we are subdividing it into smaller and smaller quadrants so that for one particular region, say for example Ri, okay, so Q of Ri is true. So if the Q of Ri should be true, so that is what we define as the condition for subdividing into smaller and smaller quadrants. So here we take the entire image and then keep dividing. So we divide the image into quadrants. If at all the Q is false for one particular quadrant, okay, so if it is true, if it is false, keep on subdividing. The time it becomes true, I cannot further subdivide because already it is one particular segment. So if it is false, keep subdividing till within that region it is true. So say for example, I took this image R, okay. So in the whole image, the q that condition will not be common for the whole image. Now the whole image cannot be one segment. So what I'll do is maybe I'll divide such that R1, R2, R3, R4. So within R1 the predicate is true. So I am not subdividing it into much quadrants. Okay. So R2 also it is true. So done. Okay. R3 it is true. So done. So subdivide. Okay. Till so that for any region Q of Ra is true. If at all Q of Ra is false, we subdivide that. For example, maybe in this case, in the R4, the quadrant, the Q condition was false. So again, I subdivided into 4 regions. Still, I get maybe again, maybe so there may be a chance that R43 maybe again not the Q may be false. Then I may have to again subdivide. But finally, the least region should be 1 pixel. Okay, so that is a condition. So this splitting technique has a convenient representation, which I have already told you, in the form of a quad tree. Okay, we should understand that the root of the tree should correspond to the entire image. So what was the root here? The root here is R, and each node should correspond to the subdivision of the node into some descendant nodes. Okay, again subdivide. So R4 is actually for me the node for which again I am subdividing into 4 subnodes. Okay, so this is how we are going for region splitting, and by now you also understood what is meant by region merging. Okay, so now I think by now you understood that we split based on some predicate. Okay, so till the predicate becomes false, we keep subdividing. Okay, but we should understand that just splitting is not sufficient, because the final partition will normally contains adjacent regions with some identical properties. For example, I told you maybe R41 or maybe R42 and R2 may belong to say one particular segment. Okay, so maybe like that. So that time I'll have to go for merging. So initially I split based on a predicate, then I may have to merge. For example, R4, R2 and R41, R42 and R2 maybe belong to one particular segment. So then I have to go for merging as well as splitting. Maybe again R2 may have to be split. So splitting, merging till we can get some the condition of segmentation is satisfied. So if two adjacent regions Rj and Rk are merged such that that union can be true, that predicate of the union should be true. Okay, so we can summarize all this into the following steps. So split into 4 disjoint quadrants such that for any region Q of Ra is false, and we go on splitting till no further splitting is possible. We go on splitting and then we merge any two adjacent regions Rk and Rj for which the condition, that is a union, the predicate of the union is true, and stop when no more merging is possible. So actually we start with splitting and finally we go for merging. So once merging is done, and if the adjacent regions, the union, if the predicate of the union of two adjacent regions gives true, okay, then we can merge them. Okay, and till no further merging is possible, we can go on merging. Okay, and also we should be very clear that we should have a minimum quad region size beyond which no further splitting can be carried out. For example, we have to define the size. Okay, what should be the minimum size of that quadrant? Okay, so whether it's 4 cross 4 or 3 cross 3 matrix. So you cannot go on doing till the worst case is 1 cross 1, that is having only 1 pixel in a quadrant. But usually it's not like that. So we have to define a stopping criteria for splitting also. So what should be the minimum size of the splitting beyond which splitting cannot be carried out? I think this kind of splitting merging, I think the idea becomes very clear by now. Also you can go through one of the example that is given in the textbook. So in this example, actually this is what our famous Cygnus loop, which I have taken many times in the module 1, right? Okay, so this Cygnus loop, so the idea here is to find the segment or the loop or the ring surrounding this Cygnus loop. Okay, so if you observe properly, this Cygnus loop is having lot of dynamic region. Okay, so it's not that all the intensity within this is true. Okay, within this is constant. So how do we define a predicate? Maybe I will define a predicate true if the standard deviation is greater than alpha. So I have to define a standard deviation here, and if the value of some m is between 0 and b, and if it is false otherwise. Okay, so here initially, this is the image of the Cygnus loop, and this figure B, C and D you can see, right? So B is actually allowing the smallest quad region to be of size 32 cross 32. Here, the smallest quad region, that criterion is 16 cross 16, and here it is 8 cross 8 pixels. Okay. So what I wanted to do is, the brief explanation of this is actually given in the textbook, which we can go through and try to analyze how they have used simple splitting and merging. So idea here is to use splitting and merging, and here the defined criteria for predicate is based on standard deviation. Okay, because of the dynamic property of the Cygnus loop intensity here. You can see the intensity here. I can see surrounding the Cygnus loop there is a kind of a ring, right? So you can see here there are a lot of deviation is the standard deviation will be very large, right? Like you can see dot dot, black white black white black white black white, like that. So I want to determine the loop. I think the condition is very simple, and so I think I told you how we can use standard deviation. Initially I have told you, right, when I started this the module on segmentation, I told you about predicate and how one of them is using standard deviation. Of course, it does not mean that always you have to use standard deviation. It's just one of them. Okay. So you can see here, and the smallest size. So here 32 cross 32 you see, here 16 cross 16. Here 8 cross 8. I think you understood the example, but you want to go and analyze it a little more further. I request you to just go through the textbook and analyze. So with this, we come to the end of the topic on region growing, region splitting and region merging. So just pause for a while and try to understand what is region growing. So region growing, we took a seed, then we went on, checking the neighborhood, or we checked the the adjacency, and we checked whether it is similar to the original pixel, and we went on growing. In splitting, what we did is we took the whole image as one entity and went on splitting into quadrants until some stopping size, and also when the predicate is false. Okay, so that is about splitting. And merging is when two adjacent regions, when the union of the two adjacent regions, if the predicate gave true, then we'll merge, else we'll not merge. Okay, so that's all is about the whole idea of region growing, region splitting and merging. Okay, so see you in the next class. I hope you have understood this video lecture. Thank you.